Welcome all to our Simplified Chemistry class. These are sessions that we want to put in place to make our students get it that chemistry is a simple subject. We want to make everything look very simple. We are starting with a very simple topic in Form 1 about air and combustion. My name is Simple Teacher. So we'll start by defining what air is. It is just a mixture of gases, and it is a mixture and not a compound because one, its constituents can be separated by physical means. You don't need to undertake any chemical process to separate the components of air. Number two, the composition changes from place to place. That's why in certain areas like in Europe you will find that water vapor is more in air than it is in Africa. Number three, the characteristics of air are just borrowed from characteristics of its constituents. That's why you find that air can be able to support combustion, while we know very well that in air it's only oxygen that supports combustion. The composition of air, 78% of it is nitrogen, 20.9% is oxygen, 1% is noble gases, and 0.03% is carbon dioxide, while water vapor is variable, the same case with dust particles. In terms of the parts of air, air can be divided into two parts. There is the active part of air, the part that supports combustion, and there is the inactive part of air, which does not support combustion. The inactive part of air is mainly nitrogen, and the active part of air is mainly oxygen. In terms of determining the percentage of active part of air, we have 4 experiments that you come across, and I want us to go through them very fast. The first one is using candle stick. In this setup, a candle is lit, and then it's put over a trough of water, and the gas jar is inverted so that the candle is enclosed inside the gas jar. You'll find that after some time the candle will get extinguished, to go off as per the second trough here, because all the oxygen inside the gas jar will have been used up. The water will also rise at the gas jar. Initially there was no water in the gas jar, but at the end of the experiment there will be some water in the gas jar. This water will rise into the gas jar to occupy the space that was occupied by oxygen that has been used in burning of the candle. So you will notice that to calculate the percentage of air that is active, you take the length of the space, or the space occupied by water at the end of the experiment in the gas jar, as a section. Of course it will be a section of the entire gas jar, so you take that section, which we can call LW, you divide by the length of the entire gas jar and multiply by 100 to get the percentage of the space occupied by water, which is equal to the space that oxygen was occupying. The percentage you should get is around 20 to 20.9, and the reason why it will not be accurate as expected is because probably not all oxygen is used up during the burning of the candle. Of course, this might be, the candle might go off even before the oxygen is used, because a lot of carbon dioxide is produced even during the burning of the candle. Using sodium hydroxide or potassium hydroxide is advised instead of water, because the hydroxides will absorb the carbon dioxide, carbon dioxide, that is produced during the burning of the candle. This experiment 2, the setup is as per the illustration in the presentation and the diagram presented here, where we have a combustion tube that has copper turnings inside. At the both ends of the combustion tube there are syringes, syringe A and syringe B. Air is pushed in through syringe B, and part of it is used for combustion of heating of copper turnings, and the remainder is pushed into syringe A, or pulled through syringe A. So what happens is that this air that is pushed through syringe B is should be pushed slowly and repeatedly, not at once. It should be done a little bit, then a little bit, then a little bit. Is because you want to make sure that all oxygen has been used up to to burn the copper. Also, it should be done slowly so that you give air enough time to react with or to have contact with the copper turnings. So what will happen at the end of the experiment or after some time is that the copper turnings will change from brown to black. As you can see, it's brown because copper metal is brown, but once heated, copper 2 oxide will be formed and it is black, so the brownish will turn to black. So the reaction there is copper plus oxygen to form copper 2 oxide. You should note that cotton wool is used at both ends of the syringe. As you can see, at this end of syringe A and at this end of syringe B, inside the combustion tube, there is some cotton wool. This is put there so that we can protect copper turnings from being blown into the syringe as air is being pushed in from syringe B. So the excess copper should be put there so that we make sure all oxygen in the air that is pushed in is used up. So if copper is replaced with magnesium in this reaction, you find that the reaction will be very exothermic, resulting in the magnesium metal reacting with both oxygen and nitrogen in air, forming both magnesium oxide and magnesium nitrate. This means that the amount of air that will be used in this combustion will be much more than expected, because both nitrogen and oxygen will be used up. Therefore, you'll find that the percentage you'll get at the end will be higher than what is expected. In terms of how to determine the percentage of active air, what you do, you take the measurement in syringe B. Remember, syringe B is the one that is pushing air in. You take the measurement at the start of heating, which we can say is V1, the volume of air in syringe B at start. Then you take the volume of air at the end, in syringe B at the end, which will be V2. This should be lower than V1 because some air have been used up. Then you get the difference between V1 and V2, which is the air that has been used up during the experiment. This we can call it V3. So to get percentage, you take V3, you divide by the initial measurement, which is V1, then multiply by 100 to get percentage. There could be some reason why there is inaccuracy, because expectation is to get 20% or 20.9 around there, but you'll find that it is never accurate in most cases. This is because probably not all oxygen has been used up during copper burning, and also there could be some leakages in the setup. Experiment number 3 is rusting of iron. In this experiment, what happens is that you wet the gas jar at the bottom there, then you sprinkle some iron fillings there, and then you invert the gas jar in the water, in a water trough. So what happens after 48 hours is that the iron fillings will turn brown due to rusting. Of course, they will have reacted with oxygen and water to form rust, which is what we call iron 3 oxide. So the level of water in the gas jar will also rise so that it can occupy the space that was being used by oxygen. So in terms of calculating the percentage of active part of air from this experiment, you take the volume of recent water, divide by the volume of the entire gas jar, multiply by 100. In this breath, we can also discuss about rusting. We have seen there are two conditions for rusting, necessary for rusting to happen. 1, oxygen must be there. 2, water must be there. The rusting equation is iron plus oxygen plus water. We form hydrated iron 3 oxide, which is what we call rust, and it is brown in color. To accelerate rusting, you need to have three conditions. One, you need to have a salty environment, you need to have an acidic environment, and you need to have high temperatures. To prevent rusting, we can do oiling, we can do greasing, we can do painting, we can do galvanizing, and we can also do tin plating. Now let us go to experiment number 4 to use to determine the percentage of the active part of air, which is burning of phosphorus. In this experiment, the setup is per the diagram shown here, and what happens here is that a gas jar is inverted in a trough of water. Then a platinum wire is coined into the gas jar. One end goes into the gas jar, and then the other end comes out of the trough. Phosphorus is fixed or placed at the end of the platinum wire, which goes into the gas jar. This is because for you to burn phosphorus, you can't do it directly. If you do it directly, phosphorus will explode. So what happens, the heating will be done at the platinum wire outside the trough, so that the heat travels inside to phosphorus. So that is how the setup is. As I've stated, phosphorus, if heated directly, will explode. That's why we are heating through the platinum wire. The observation after some time of heating is that white fumes will be formed around phosphorus as phosphorus reacts with oxygen on heating. This results in formation of phosphorus 5 oxide and phosphorus 3 oxides that are white in color. That's why the color fumes will be formed inside the gas jar from around where phosphorus is. The fumes then will disappear as the oxide is absorbed by water to form phosphoric acid. So the water will also rise in the gas jar, as you have seen, to occupy the space that was left by oxygen that has been used in burning of phosphorus. One precaution you should put in place when doing the experiment is that you should avoid inhaling the fumes of phosphorus 5 oxide and phosphorus 3 oxide, because they are poisonous. To calculate now the percentage of active part of air from this experiment, you take the length of gas jar not filled with water at start, which is Y, as you can see here, and then you take the length of jar not filled with water at the end, which is X. So then you can get the difference, so that you know what length is used has been occupied by water, which is now Y minus X. So whatever you get as a difference, you divide by the length before at the start of the experiment, which is Y, and then multiply by 100 to get the percentage. It may not be accurate, of course, like others, because not all oxygen will probably react with the phosphorus, and therefore maybe some oxygen will remain. Now we go to, those are the 4 experiments that you need to understand about determining the percentage of active part of air. We move now to establishing an experiment to establish the presence of carbon 4 oxide in air. This is done through a setup like shown in the diagram I'm presenting, where water is forced into the flask, maybe water from the tap, and then when the water is forced into the flask, air is pushed from the flask now to the boiling tube, where fresh lime water is contained. So, and then there is some paper cover up here at the other opening of the boiling tube, just to ensure that no air enters the boiling tube. So now, after this observation, after some time, you find that a white precipitate will be formed in the boiling tube. This is because the carbon 4 oxide from air that is coming from the flask will react with lime water. Lime water is calcium hydroxide, to form the insoluble calcium carbonate, which is white. That's why a white precipitate will be formed. So the reaction is carbon 4 oxide plus calcium hydroxide to form calcium carbonate and water. Then on excess bubbling of air, if a lot of air continues coming into the boiling tube, this precipitate will dissolve because there will be formation of calcium hydrogen carbonate. Remember, water is being produced also, so this water will react with the formed calcium carbonate to form calcium hydrogen carbonate, which is soluble. That's why the precipitate will dissolve after some time. This is a confirmatory test for carbon dioxide. This test is that once, wherever you react carbon dioxide, or you bubble carbon dioxide into the lime water, or calcium hydroxide, a white precipitate is formed. Or commonly, what we say is that the carbon dioxide turns lime water milky. So another experiment that you need to know about is on establishing the presence of water vapor in air. This is done through pushing of air into a U-tube containing anhydrous calcium chloride, as shown in the diagram. You'll notice that when air is pushed here into the U-tube, a solution is formed. This is because water in air reacts with anhydrous calcium chloride to form that solution. So at the end of the day, there will be a solution formed. Next, we look at oxygen as another major subtopic in this topic of air and combustion. Remember, we said oxygen is the active part of air, and it comprises 20.9% of air. There are three ways through which you can prepare oxygen in the laboratory, and one of the ways is decomposition of hydrogen peroxide. This is done as per the setup I've put in the diagram, and this, as you can see, there is a dropping funnel where hydrogen peroxide is through which it's put into the flask. Inside flask there is manganese 4 oxide. So once the hydrogen peroxide is added, there is a rapid bubbling, and this bubbling results in creation of a gas that moves through into the trough where there is a gas jar inverted. This gas then bubbles into the gas jar through the water, over the water. So this gas is odorless and colorless. This is oxygen, of course, and it is collected through over water, or downward displacement of water. The reason why this is possible is because oxygen is just slightly soluble in water, and it is also less dense than water, so it can rise above water. This gas can also be collected through upward delivery because it is also less dense than air. So what happens here is that hydrogen peroxide is broken, or it is decomposed into water and oxygen. So manganese 4 oxide, which is is a component inside the flask, and it is just used to fasten, to enable the decomposition of hydrogen peroxide. So hydrogen peroxide alone cannot decompose, so it requires to have a catalyst like manganese 4 oxide, which will force it to decompose and do it very fast. So manganese 4 oxide is a catalyst. Remember, a catalyst is a substance that is used to alter the rate of reaction without getting used itself during the reaction. So in this case, manganese 4 oxide remains, it's not being used, but it hastens the process of decomposition of hydrogen peroxide. So the equation is that hydrogen peroxide in the presence of manganese 4 oxide decomposes into water and oxygen. So to test confirm that the gas produced is oxygen, you can lower into the gas jar a glowing sprint, and you will find that it will get rekindled or relighted. It will just relight and get rekindled, because oxygen, as you know, is a necessity for any burning, so it will relight, rekindle the sprint. So method 2 of preparing oxygen in the laboratory is use of water and sodium peroxide. As you can see in the setup, sodium peroxide is down here inside the flask, and then water is being dropped down using the dropping funnel. In the same case, in the case like previous, the when water is added, there will be rapid bubbling, and then the gas will be collected through of a water like it was the case in the previous preparation method. So method 3 is heating of potassium chlorate in the presence of manganese 4 oxide, as you can see in the setup. So in this case also, manganese 4 oxide is just a catalyst. The only item that is being heated here, which is reacting, which is being decomposed, is potassium chlorate. Manganese 4 oxide is just a catalyst. So in the setup, the similar case happens, and the gas is produced, oxygen, which is collected through of a water or downward displacement of water. The equation is potassium chlorate in the presence of manganese 4 oxide and heat. It produces potassium chloride and oxygen gas. Manganese 4 oxide, as I've said, is just a catalyst. In the industrial production of oxygen, mass production of oxygen, this is done through a process called fractional distillation of air. It has its own process, and it is as per the setup, or it's summarized in the chart that I'm presenting here in this diagram. So you'll see that air is pumped into filters being the first chamber in the process, where dust is removed through filtration. Once dust is removed, air without dust now goes into the absorption tower, where we have concentrated sodium hydroxide inside there. The sodium hydroxide absorbs carbon 4 oxide. So now from absorption tower, the air is pushed into coolers without now carbon 4 oxide and without dust. In the coolers, where the temperatures are -25 degrees centigrade, the water vapor is removed. And once water vapor is removed, the resulting air without water vapor, without carbon 4 oxide, without dust is moved into compressor. At the compressor, the air is liquefied, and helium and neon are removed. So now, from the compressor, the air that goes into the fractional distillation chamber doesn't have neon and helium, doesn't have water vapor, doesn't have carbon 4 oxide, and doesn't have dust, and it is also liquefied. At the fractional distillation chamber, the three gases are distilled. At -196 degrees centigrade, nitrogen is the first to be distilled. Then argon is distilled at -186 degrees centigrade, and oxygen is distilled at -183 degrees centigrade. So now we go to the physical properties of oxygen. 1. Oxygen is odorless. 2. Oxygen is colorless, no color. 3. Oxygen is only slightly soluble in water. That's why it is you are able to collect it through of a water method. 4. Oxygen is less dense than water and air. That's why you can collect it through upward delivery. The chemical properties of oxygen. First, we look the main properties. 1, we look at the reaction with non-metals. Basically, there are 3 non-metals that oxygen commonly reacts with, and these are phosphorus, sulfur, and carbon. The reactions are, of course, through heating. So what happens here is that there is also reduction of mass. Once these non-metals are react with oxygen, gaseous oxides are formed, and these gaseous oxides are able to escape into the air. And that's why in the final product there is reduction in mass. In a summary, if carbon is heated in oxygen, excess of oxygen, carbon 4 oxide, is formed, and if there is only limited oxygen, carbon 2 oxide is formed. Both are colorless. If sulfur is burnt in oxygen, sulfur 4 oxide, which is colorless but misty, is formed. If phosphorus is burned in oxygen, phosphorus 5 oxide, which is white, is formed in excess oxygen. And if the oxygen is limited, phosphorus 3 oxide, which is also white, is formed. Now we look at the reaction with metals, or burning of metals. So if metals are burnt in oxygen, solid oxides are formed. There is increase in mass. The reason why there is increase is because there is addition of oxygen to the metal, and therefore the resultant solid will have gained some weight, some mass. So in a summary, if sodium is burnt in oxygen, sodium oxide is formed, which is white. And if there is excess oxygen, sodium peroxide is formed, which is yellow. If calcium is burnt in oxygen, calcium oxide is formed, which is white. If copper is burnt in oxygen, copper 2 oxide is formed, which is black. And if magnesium is burnt in oxygen, magnesium oxide is formed, which is white. Note that when reactive metals, the most reactive metals, which are sodium, potassium, calcium, and magnesium, burn in air, I'm talking about air here, not oxygen. If they burn in air, both oxides and nitrides are formed, because there is now reaction, because these metals are very reactive. So there will be a lot of reactivity, and therefore both oxygen and nitrogen will react with the metals. So once the metals react with oxygen, they form oxides, and once they react with nitrogen, they form nitrides. That's why whenever they react with air, nitrides and oxides are formed. So the oxides, while dissolved in water, they form hydroxides. So when they react, the oxides react with water, metal hydroxides are formed. But when nitrides are reacted with water, both the hydroxides are formed and ammonia gas. So in case of nitrides, hydroxides and ammonia gas are formed. So in a summary, metal oxide plus water is metal hydroxide, results in metal hydroxide, while metal nitride plus water results in metal hydroxide and ammonia gas. Let us now talk about oxidation, reduction, and reactivity series. So oxidation is gaining of oxygen. For example, when magnesium reacts with oxygen, it forms magnesium oxide. It gains oxygen to form magnesium oxide. So there is oxidation. Reduction is losing or donating of oxygen. For example, if copper 2 oxide reacts with potassium, potassium is more reactive than copper, there is formation of potassium oxide. So what happens, potassium gets oxygen from the copper 2 oxide and forms potassium oxide, while copper loses oxygen, so it remains as copper metal. So in this case, there is reduction on the copper side and there is oxidation on the potassium side. Reducing agent is the element that makes another to lose oxygen. Like now, the way I've explained, potassium will make copper lose oxygen. So in that reaction, potassium will be the reducing agent. The oxidizing agent is the one that makes another gain oxygen. Like in that case of my example, copper is the one that is giving oxygen to potassium. So copper is the oxidizing agent. Redox reaction is a reaction where there is both gaining and losing of oxygen. Like it has happened here, potassium has gained, copper has lost, so it is a redox reaction. In terms of reactivity series, this is the determinant of who gains, who loses. Reactivity series gives us a list of elements, common elements, and their strength in gaining oxygen. That's their affinity for oxygen. We refer to it as affinity for oxygen. In this list, potassium is the highest, so it has a very high affinity for oxygen. So if it reacts with any other metal oxide, it will deprive that metal of its oxygen. Then there is sodium number 2, there is calcium, there is magnesium, aluminium, carbon, zinc, iron, tin, lead, hydrogen, and copper. Let us make it simple by having an example. Heating of magnesium and copper oxide. As you can see, magnesium is number 4 in the reactivity series, while copper is number 12 in the reactivity series. So when they react, magnesium will get oxygen from copper oxide to form magnesium oxide, and copper will lose oxygen and remain as copper metal. That's why there is a color change. The oxide changes from black, copper 2 oxide is black, to brown, now copper, which is brown, as it is reduced to copper metal. So there is reduction. Then a white solid is formed as magnesium gains oxygen to form magnesium oxide. That is oxidation. So copper is the oxidizing agent here, while magnesium is the reducing agent. The reaction is redox because there is both gaining and losing of oxygen. So uses of oxygen. One, it can be used in hospitals by patients, like it was during corona time. Patients with breathing difficulties used to be assisted by being linked into or connected into oxygen, so that they are able to breathe, or they are able to get oxygen even without having capability to breathe. Number two, it can be used in welding and cutting of metals. And number three, in the manufacture of rocket fuels. Maybe the final thing we can look at is sample questions, or questions that have come in the KCSE in the past from this topic. I want you students to be able to look at them, then finally we'll go through them together and be able to look at the answers together. But for now, you can see in the 2021 paper 1 chemistry KCSE, we are given some apparatus there. There is iron fillings, there is 100 milliliter measuring cylinder and trough and water, and you are told to draw a setup to investigate the percentage of air used when rusting. That one is simple, we have gone through such a thing. Then you are told to write an expression to show how the percentage of air used is calculated at the end of the experiment. That one should be very simple. In 2022 paper 1, there was a question on your students were required to give a reason why painting or galvanizing iron sheets protect them from rusting. And then B, there was explain the advantages of galvanizing of a painting of iron sheets. Go through them, look for the answers, and then we'll discuss later at a later session. Then there was another one, the setup. This was in 2013 paper 1, setup to use to prepare oxygen. And of course, this one we have gone through. You are supposed to study and answer the questions. Number 1, identify X. Then the property of oxygen that makes it possible to be collected as shown, and the uses of oxygen. This is simple. Then 2018 paper 1, there was you are told using iron filings, describe an experiment that can be conducted to show that oxygen is present in air. That should be very simple. So with that, we come to the end of this session today, simple chemistry, and I think I've made it very simple. It's become very simple, the topic of air and combustion. We want to make chemistry simple, 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 and simple again. Thank you very much. Simple teacher will see you in the next session. Thank you.